I'm Gerald Rogers with Intel. I'm a software architect in the network products group, focused primarily on open vSwitch DPDK. And so we're here to talk about DPDK optimization techniques and then some of the enhancements we made in open vSwitch and in some little bit of performance data that we have published recently for our open networking platform. So this is our usual legal disclaimer. It has to be in every presentation we present, so it's here. So for Open vSwitch 2.4, which came out, we had focused a lot on performance enhancements and improvements to the DPDK Netdev implementation. So with the 2.4 release, we showed that 5-to-5 performance at 256 bytes, we were able to achieve 40 gigabits per second on a single forwarding core. So if you compare that to basically stock kernel type OVS, it's about 12 times the performance that we were able to demonstrate with the Netdev DPDK implementation. In addition to the performance enhancements, we added in support for vhost queues and vhost queues improvements, vhost user, open daylight and open stack detection was also integrated. We showed the ability to do link bonding as well as improvements in the mini-flow performance. And we fixed some of the vhost retries and some other little things within the forwarding path that impacted the performance. So our primary focus for this release was performance. So the key areas we looked at were we made an alignment change in the vhost code. There were some packet alignments that weren't quite correct. We enabled the vector pull mode drivers in the physical ports. And then we increased some of the EMC cache as well as fixed a bug that was in mini-flow that impacted the performance. Okay. So when we do performance analysis or performance testing and reporting, we use our open networking platform. This is a reference platform that we have for NFV type workloads. And it's there to enable kind of like an open ecosystem for IA and such. So, but it's the basis for all of the performance data that I'll show here in just a second. So, okay, sorry, that one was hidden originally. So, okay, so for Open vSwitch 2.4, basically for our performance numbers, the platform we use is a Haswell it's a Haswell 2.6 system, which is an E5 2697 v3. And so this kind of gives you a little bit of the reference platform that we use for performance testing. And here we go. Here's a little bit of performance data. So this is a physical to OVS, to physical performance throughput that we took. This is all in the ONP 1.5 performance report. And you see for 64-byte packets over here on the left-hand side, we do about 16, 17 million packets per second for a single core. Dual core, we push about 30 million packets per second. And then with a 4-core system, it's about 48 million packets per second on small packets. So, and then basically reach line rate, on 4 cores at about 128 bytes. So that's basically coming into OVS and then looping back out onto physical ports. Okay. So in our PHY to OVS to VM to PHY and back down to OVS into the PHY, if you look at this one does a comparison between stock OVS, which in the kernel, which is about 1.3 million packets per second or so. And with the changes that we've made, you can see with a single core about 10 million packets per second of throughput. And then with a 2-core system, it's upwards of 18 million packets per second of throughput to virtual machines with the performance enhancements that we've made thus far. Okay? Yes, of course. Yeah, yeah. So anytime we would do with DPDK VM, it's DPDK inside the VM because we're testing the vSwitch performance. So we want to show the best performance of the vSwitch. Anytime you go to a particular application, it's of course not going to be quite this high, depending on the application that you're running. So, okay. So this is actually pretty recent data. This is VXLAN tunnel. Oh, I forgot to mention one thing here. These numbers are aggregate switching rates for 5VM PHY. And what we mean by aggregate switching is that you're actually performing 2 switching operations on the core. One switching operation going into the VM and another switching operation going back down. So you actually, so that's the reason why it's considered an aggregate. So for tunnel PHY performance, you see that the stock kernel is, I don't know, a few hundred K. And then we push about 7.7 million on a single core with VXLAN tunneling. The setup here is we use Ixia as our traffic generator on all of our tests, but here we're actually using Ixia as the VXLAN generator as well. So Ixia emulates the VXLAN and does encapsulation for you. And then we set it up according to the OVS configuration for VXLANs. And then we terminate into the VM, and then we come back down. Now, again, in the VM, it's also a DPDK application. So one core, we're about, what did I say, about 7.7, and then 2 cores is about a little over 14 million or so packets per second. It's a little hard for me to read. So that's kind of our tunnel performance. So what are we doing going forward? So we're looking at further enhancements for performance perspectives as new products move along and bandwidths go up and higher performance is required. So we're looking at a few techniques in the VirtIO and vHost interfaces. Actually, some of these patches are already out onto the DPDK mailing list. We made a change to the guest VirtIO driver to put things into an ordering, a fixed order. Works for DPDK VirtIO, and it's there to basically reduce cycle counts associated with processing. In vHost, we have a bulk allocation for MBUFs. That patch that has gone out to the DPDK mailing list. We're also making the vHost change in the vHost driver to use bulk allocations. DPDK, well, MJ here, we'll get into it a little bit later, but anytime you do bulk allocations with DPDK, you reduce cycle counts in terms of locks. And so that's one of the things we're looking at. We're also looking at a 0 copy receive on the vHost side. So we basically avoid 1 copy coming out of the VM, and we can pass that through the system. In terms of the forwarding implementation, we're looking at a vector tuple extractor, basically trying to look at how we can take advantage of the AVX instructions to speed up the parsing of packets, and using DPDK hashing such as cuckoo hash. And then implementation of variable key hashes, so that to speed that up. Right now, we just kind of started looking at tunnel processing to see if there's a way that we can improve the tunnel performance. A little bit later on, Nan Daly will discuss some of the hardware accelerations that we're looking at. Primarily in the match action, which then would interface into some of the hardware components and provide a device agnostic match action control interface. So it's basically to accelerate into the software switch and such. Okay, and I think that's it for me.
Okay,
MJ,
thank you.
MJ will take over.
Thank you very much. How much time I have?
You have 10 minutes.
Okay, great.
10 minutes.
Thank you very much. Am I on? Okay, great. So my name is MJ. So we are going to now. Okay, Gerald right now took us to the OVS at top level, right? You saw the benefits what you are getting with DPDK. Now we are going to open the hood and we are going to go inside and see what techniques DPDK does in terms of giving you the performance. So what we are going to look at is what is the problem statement and what tools we have in our hand, right? So when we talk about CPU, cache and bus and PCIe and everything, what are the tools we have and what type of latency we are talking about and how are we going to address the problem statement. So that is what we are going to go through. We are going to go through very fast, so listen fast. And so the first thing is we are trying to, we are entering into the world of paint the NFV world with DPDK, right? If you want to paint the NFV world with DPDK, does DPDK support many architectures or only one architecture? So how many people know that DPDK supports more than one architecture? Okay, can you just yell out a name, yell out a number? How many architectures it supports? 2, 4, 5. Okay, can you tell the names? What are the names? IA, Power, ARM. Both two kinds of ARMs. Okay, only one kind of IA, but two kinds of ARM. Okay, and then Power and what else? Okay, let us look at it. Right. So you have IBM, Power, Freescale, Easy Chip, and then ARM by Cavium. Lot of good efforts are happening, and the credit goes to community, right? And so on the NIC side, right, you are able to see Broadcom, Chelsea, Cisco, VNIC, and Emulex and Mellanox. So all these things are supported, and then you see the Intel NICs. Okay, so this is the big picture, the block diagram. So you can see various components. Some of the components are to do with the network components. Some of the components are to do with the as Gerald was talking about, right? The if you are building a router, you have some components for that, and if you have building a security, you have components for that. So all the software components are there. For example, ACL API, QoS API, crypto API. So you can look at that. So now question, right? So in network we talk about only two things, right? Mainly latency and throughput, right? So do you have numbers? Do you have performance numbers, or do you have a credibility or a testimonial? Right? You from Intel will talk about great things about it, but is there a third party testimonial for latency and throughput, right? So my question back to you is, do you give good credibility to academics like MIT and CMU, right? So these are the two who gave their credentials. So let us look at it, right? So if you are going to optimize for throughput, you heard Raja talking about we do bulk, so thereby throughput can be improved. But are you trading off latency? That's the normal thinking we will have, right? If you are doing a lot of throughput, are you trading off latency? So let's look at the latency testimonial. So if you go on Google and search for MIT fast pass, you will find out that they are dreaming about a network with 0 queues. That's possible because of the low latency that's possible with the fast service that DPDK provides. But we are going to get into how that is done. Okay, so what is the task at hand? So you are having a packet coming in, right? And then you need to go and look at the packet to do whatever you want to decision making, and then you want to do the activity. So if you are looking at 40 gig, the inter packet arrival time, you are talking about what? 60 nanosecond. So if you convert it into 2 gigahertz processor, 2 gigahertz is how many picoseconds? Anybody? What is the picoseconds count for 2 gigahertz? 500? Okay, so with that you are talking about only 19 cycles you have for RX and only 28 cycles for TX, even if you do not do much work. So that is the problem at hand, right? Which means you are going to receive, process and transmit. By the time the next packet comes, you have only that much cycles. Now to handle that type of speed, what kind of tools we are operating with? What is the latency of the devices instruments or devices we are operating with? So this talks about everything being in the user space, because you don't have the luxury to do the kernel to user transition. You don't have a luxury to take an interrupt because your lifetime purpose is to babysit that port and poll the port. So that's the type of scenario you have. So what are the things that DPDK eliminates, and what is the technology or what is the microarchitecture techniques it uses to eliminate those problems? So there's no, as I said, there's no interrupt context switch because we use polling. There is no kernel user overhead because we are doing user mode driver. And again we use POSIX thread affinity thereby there is no interaction from the Linux scheduler, right? So you are getting the full attention of the core to the task at hand. And similarly, Linux comes by default, 4K paging, but even though of late, like the Linux does have the huge page support, but we use a huge page, thereby you don't have the problem of page misses and other things. And then lockless communication is another mechanism, and then high throughput. So that is the way we go with. But let's look at the latency, right? You have L1 cache. If you are getting a hit, you are talking about 4 cycle latency. For 19 cycle receive budget, 4 cycles seems to be fine. But what if there's a L1 cache miss and then L3 cache hit? We are not even talking about memory. We are not even talking about all the cache being missing. We are talking about last level cache hit. The cycles is 40 cycle latency. With the 40 cycle latency, how are you going to achieve 19 cycle? That's the problem at hand. So how do we solve? And these are the various steps. You will have files. I've been already shown 5 minutes to complete it. So the point is, what we do is we amortize. Instead of going for one descriptor, we go for 10 descriptors at a time. So you go for bulk. Even at that level, you go for bulk. So when you go and take 10 descriptors, now you amortize the overhead across that, right? So that is one thing. So similar things we do. And then let me just complete with 2 more things. So we talked about the CPU nowadays go and gets cache line. They don't get if a software is asking to get a variable, it doesn't go and get a 8-byte or 16-byte variable. It goes for a cache line, which means let's say your variable is sitting across 2 cache line. So let's say this is one cache line and this is another cache line. But let's say your variable is straddling across 2 cache line. The CPU will end up fetching 2 cache lines, right? Because your variable is straddling across 2 cache lines. So it is your responsibility to write such a way that everything is cache aligned, and you want to not pack a lot of things together. You want to keep enough distance from one variable to another variable, at least one cache line. Thereby you can achieve the parallelism. Okay. So I think we have a lot more to cover, but anyway, I just gave you an idea of how the things are done under the hood so that you get the benefit from DPDK. Okay, I think we are done. Thank you very much.
Well, thank you. You're such an excited, animated speaker. It was a lot of fun to watch you. So we have times for some questions. I'll move the other handheld mic over to here so that it's easy for everyone to ask questions. Thomas, go ahead.
Sure. I think I'm just asking the obvious question. What's your answer to containers?
So yeah, for containers, there are some projects that we are investigating right now in terms of how to interface into containers. Right now, it's pretty preliminary to discuss exactly what we can find because we basically just kind of started it.
Can I ask a question? Why are containers hard?
Well, but basically because you need to end up queuing into the socket, which is a kernel-owned buffer. The packet is in user space, so the obvious path would be through KNI back into the kernel. That's kind of introducing the slow path again.
Yeah, that's one way to look at it. Yeah, but there are some alternatives that could be done.
All right, and then maybe go ahead.
I had a question for both of you actually, which is, are you anticipating that DPDK will actually drastically improve the container performance? Since it's not the same thing that's sort of limited by a NIC, it's kind of software to software, and there are certainly opportunities for reducing things like buffering and copying. But are you expecting that it would drastically improve the performance the way it has with hardware and with VMs?
You mean with VMs?
Yeah, well, VMs attached to physical NICs versus sure. Containers attached to VMs attached to physical NICs, or VMs attached to basically tunneled physical NICs versus VMs. Well, I guess in this case, in your full stack example, you had virtual NIC in the VM switched twice to a physical NIC. So I guess the question is, would you expect the same sort of performance improvement that you saw with virtual machines with containers, or would you not because you're kind of hardware limited in the physical NIC case, and you're sort of not in the container case today?
Well, so in the container case, right, so the biggest issue right now is going through the vEth interface in the container, right, because that's where everything ties in. There are ways to, if you wanted to pass the NIC up into the container and run DPDK in a container environment, that's possible.
It should be identical pretty much to the
Yeah.
to the out of container version. But yeah, I'm talking
Correct.
to the virtual interface, although not necessarily through a VETH pair. It could be something closer to like the OVS patch interfaces or something.
You could, yes. You could, I mean, one possible is to look at vhost, right? And possible way to put vhost in the container. That's an option, but it's a little bit more complicated than just simply doing that. But we have been investigating it, but I don't know what currently the level we are at yet.
I'd definitely like to see it as well, though.
Yeah. Well, you're not the only one. There's a lot of people.
Bob, I had to cut you off earlier, so you can ask a bonus question now.
Yeah. Bonus question.
Any plans to have a PMD driver for containers? So you can have userland to userland. So basically, you put a ring between a two userland program, and you don't care about kernel.
Yeah, I mean, that's another thing you could do, right? But the only thing you run into is the namespaces and sharing namespaces between containers is what I would expect. So.
Maybe just to give a different angle, many people will expect to run unmodified container images. I think that's where it starts getting complicated.
Yeah. Yeah. Well, yeah. They even want to do that in the VM too, right?
Yeah.
So that's the advantage we have in the VM is VirtIO interface is the standard, and we can put underneath the covers with vhost. It's a little bit more complicated with VE.
Do we still have time for another question?
Please go ahead.
Yeah.
So like something very different. Given we already have bulking, an obvious next step would be like parallel flow table lookups with a single look up multiple flows in a flow table. I think there's a paper around cuckoo hash which shows impressive numbers. Is this something that you have looked into, or something that you might look into?
Yeah, so that's one thing that I am looking at, or we are looking at, is how we can integrate cuckoo hash into the processing line, the pipeline. I mean, cycle-wise, table lookup and tuple extraction are the larger cycles at the moment, at least for small packets. Of course, if you get larger packets, from a VM perspective, copies will consume, but for small packets, it's the table lookup.
So out of the two testimonials, right? MIT we talked about, the CMU testimonial is exactly what you're talking about, right? Cuckoo hash. Yeah.
So OVS does contain a cuckoo hash implementation. I don't know whether we're talking about something else here.
Yeah, this is a DPDK cuckoo.
Oh, okay. So this would be in DPDK
It
rather
would be
than
in
the
DPDK.
core of OVS.
Yeah.
Okay.
Right.
Any other questions? We have time for one more, as long as it's quick.
One more question. So
Yeah.
you mentioned this DPDK is tested in both VM and the hypervisor. So do you have data to compare that DPDK is enabled only on the hypervisor, but not in the VM? So what's the speed up in that case?
So you mean DPDK
In your
OVS?
in your test case, so you mentioned that DPDK is in both VM and the hypervisor. Is that true? So I want. So do you have the data that to compare when DPDK is enabled only in the hypervisor but not in the VM? In that case, what's the speed up?
So you mean using, say, Linux in the guest instead of
Yeah,
DPDK?
so in the VM, just use the original normal.
Yeah, no, we haven't run. Well, we may somewhere, but it's not actually one of our standard reports at the moment. So,
Thanks.
yeah.
All right, let's thank our speakers one more time.